Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. We are still in chapter 2, basic probabilities. In the previous lectures, we talked about the random experiment, the concept of the random experiment. We talked about the sample space. We talked about events. We talked about basic operations we can do on sets like intersection, union, and complement. We talked about basic probabilities, including the axioms of probability, and we talked about some basic probability rules like probability of the union, including examples, of course. Today we are continuing our discussion with a new concept called conditional probability. Now, to understand the meaning of conditional probability and its notation, the way we express it, I'll add my own comment or my own note here. So basically, we are using the following motivating example. The random experiment that we have in mind is you take a course like this course, Random Signal Theory. You take a course. This is our random experiment. Now, for this random experiment, let's define some events, not one, but multiple events. The event that you study well, and let's call it S. So S is the event that you study well. Of course, it's not guaranteed that everyone studies well. Some circumstances could happen, so you may end up not studying well. So S is the event that you study well. A is the event that you obtain an A in the course, that you obtain the letter grade A in the course. So we have S and A, two events. The event of studying well, the event of getting an A in the course. Now let's distinguish between marginal probabilities. When we say marginal probability, we mean the probability of an individual event not related to anything else. And this is what we have been talking about in the previous lecture. So for example, we say the probability of S. This means the probability that you study well in the course. So when we calculate the probability of S, we mean what is the probability that you study well in the course. The probability of A is the probability that you receive an A in the course. So we talk about the probability of S, the probability of A. So as you notice, the probability of individual events not related to any other event. This is what we call the marginal probability, the normal probability that we have been talking about in the previous lecture. Now, as opposed to this, we have also the conditional probability, الاحتمال المشروط, the conditional probability, and we use the notation probability of A given S. So if A comes before S here, the probability of A given S. What we mean here basically is the following. We mean that given that S has happened, what was event S again? S is the event that you study well. Imagine that the course has finished and I observed a particular student throughout the semester, and I noticed, I know already that this student has studied well in the course. So this event has occurred, it has happened already, and I know that. Now I'm asking myself, what is the probability that this student will get an A in the course? So again, the probability of getting an A given that. So this vertical line, we read given that the student has studied well in the course. Again, the notation probability of A given S means the probability of getting an A in the course given that you have studied. So we know already that you have studied. We calculate the probability of getting an A given that we have studied. So what is the difference between this conditional probability and just the probability of A, the marginal probability? Now, just the probability of A means what is the probability that the student gets an A regardless of studying or not. So whether the student has studied or not, what is the probability of just getting an A regardless of the study event? But this conditional probability means that I know that the student has studied. I know the student has studied, so this event has occurred, it has happened, and I ask myself what is the probability that the student will get an A in the course. Obviously, this probability of getting an A might not be the same value as the probability of getting an A given that you have studied the course. We can also define the opposite conditional probability in which S comes before A, and what this means is the following: the probability of S given A. Now what that means is the following: the probability of having studied in the course given that we know that we got an A. Now what this means is you can imagine the following. Imagine again that the course has finished and the final exam has been taken and the grades are out. So I check the list, basically the list of student, or I check the file of grades and I pick a student who has an A or A. So I know that this student obtained an A in the course. I know that this student obtained an A in the course, but I don't know if the student has studied or not. So I want to calculate what is the probability that this student has really studied in the course, given that they obtained an A. So again, the conditional probability, the probability of getting an A given that you have studied, or the probability that you have studied given that we know that you obtained an A. So this is the conditional probability. Now in this slide, what we focus on is basically the meaning of the conditional probability and how we express it. So the notation and the meaning, probability of A given S or probability of S given A. Now how do we calculate conditional probabilities? The way we calculate conditional probabilities, we use basically the definition of the conditional probability, and the probability of A given S is by definition the probability of A intersection S. Intersection again means and, so the probability of getting an A and having studied at the same time, the probability of A intersection S, and then divided by the probability of S, normalized by dividing by the probability of S. We always divide by what comes after the condition here, the probability of A given S. It is again the probability of A intersection S, both of them, divided by the probability of S. Likewise, the opposite conditional probability can be calculated by the same idea. It is again a definition, and if we just extend the idea, it is not hard to understand that the probability of S given A is the probability of A intersection S, but divided by the probability of A. Of course, A intersection S is the same as S intersection A, so on top here in the numerator, we always see the same thing, the probability of A intersection S, but here in this case we divide by the probability of A. Now, so this is a definition. This is how we can calculate a conditional probability. So you can think of this as number 1 and this is number 2, and both equations are used to calculate some conditional probability. Now, if we use any of the equations, we can use any of the equations to come up with a formula to calculate the probability of the intersection, the probability of the intersection. Now, if we take the first equation and we multiply both sides by the probability of S here, we multiply both sides by the probability of S, you will notice easily that we have the probability of A intersection S on one side, and on the other side we have the probability of A given S times the probability of S, and this is precisely what you see here. So this form here, this formula, is just another form of this one. It's an equivalent form of the first equation. However, its usefulness is basically that we can use it to calculate the probability of A intersection S. In the previous lecture, we have seen formulas for calculating the union, probability of the union. Now this is again a formula to calculate the probability of the intersection, which uses the conditional probability. Again, the probability of A intersection S is equal to the probability of A given S times the probability of S. This comes from the first formula. We could have obtained another equivalent probability for the intersection using the second equation, using the second formula, and by multiplying both sides by the probability of A. Obviously, if we multiply by the probability of A, we have the probability of A intersection S is equal to the probability of S given A times the probability of A. Probability of S given A times the probability of A. So it is easy to remember. We always have a conditional probability multiplied by the marginal probability, and it is the marginal probability of the event after the condition. A given S times probability of S, or S given A, as you see here, times the probability of A, times the probability of A. And as you notice, these are two equivalent formulas that give us the same thing. Both can be used to calculate the probability of A intersection S, and we call it the multiplication rule. So what is the multiplication rule? It is a formula for calculating the intersection probability, and that formula depends on the conditional probability, and we call it the multiplication rule because we have a multiplication operator. So the first term is multiplied by the second term. We have a times operation here. So the question you may ask me, if I need to calculate probability of A intersection S, which formula do we use, 1 or 2? The answer is simple. It depends on what is given in the question or what is given to you. Are these things given? Probability of A given S and the probability of S, we use the first equation. Or if these things are given, the probability of S given A and the probability of A, then we use the second equation. So it all depends on what is given in the question. Here in this slide, we have a similar motivation to the meaning of the conditional probability, but I find this motivational example that uses the experiment of taking a course and the events of studying well and obtaining an A, I find it easier to understand. So let me move on. And as you see here, basically, again, this is the definition of the conditional probability. We have seen it in my notes slide. So if we have two events A and B, two general events A and B, the probability of B given A is the probability of the intersection divided by the probability of A. I think it's very easy to realize that the probability of A given B is also the probability of the intersection, but divided by the probability of B. So this is what you see here is the definition of the conditional probability, and what you see here is the multiplication rule that we have covered already. So if we just take it from here and multiply both sides by the probability of A, it is obvious that we are getting this. The probability of A intersection B is the probability of B given A times the probability of A. Or if we take it from the other formula, like the probability of A given B. The probability of A given B is the intersection divided by the probability of B this time. So if you multiply by the probability of B, we are getting this form, which is the probability of A given B times the probability of B. The multiplication rule, the probability of the intersection is equal to a conditional probability multiplied by a marginal probability. Now, the best thing to do here is to look at an example. So what is this example about? The example says the following. So here in this example, we have a manufacturing process. So we have a factory that manufactures what the problem says. It manufactures high RPM pistons. So basically this is part of the car engine. However, solving the example itself, solving the problem itself does not rely on knowing this. It's not really necessary. So we have a manufacturing process, but what matters here is that this manufacturing process has two stages. So to manufacture our item, we have to go through stage 1 and then through stage 2, and both stages have to be successful. So we have some probabilities that each of the stages is successful or unsuccessful, and we have some probabilities given. So in the first sentence, we say the probability that the first stage of the manufacturing process meets specification. So the probability that the first stage is successful is 0.9. The probability given that the first stage is successful, the probability that the second stage is successful is 0.95. Now what is this 0.95 again? The 0.9 was a marginal probability. It was simply the probability that the first stage is successful. Now what is this 0.95? Is it the probability that the second stage is successful? Just the second stage is successful? I think you can answer me. The answer is no. This is a conditional probability. The 0.95 is the probability that the second stage is successful given that the first was successful. Given that we know the first is successful, the probability that the second is also successful is 0.95. Now, what we need to calculate in this question is what is the probability that both stages are successful? What is the probability that both stages meet specification? So what is the probability that the first is successful and the second is also successful? To be able to solve the problem easily, we can just define two events here. We define event A and event B. So we let A denote the event that the first stage is successful, and we let B denote the event that the second stage is successful. And what we need to get at the end is the probability of A intersection B. Obviously, what is the probability that both of them, the first and the second, and is an intersection? So the probability of A intersection B. How can we calculate the probability of A intersection B? What is the only thing that we have learned to calculate an intersection probability is by using the multiplication rule. And the multiplication rule states that the probability of A intersection B is the probability of B given A times the probability of A. Do we have these things given in the question? Yes. Probability of A, probability that the first is successful is 0.9. Probability of B given A is the probability that the second is successful given that the first is successful, which is 0.95. So we just multiply these two numbers, 0.95 times 0.9. It gives us 0.855, and this is the probability that both stages are successful. Now, what you may ask me is the following. the probability of the intersection has also another formula. So if we go back, we have two alternative formulas. So the other formula says the probability of A intersection B is the probability of A given B times the probability of B. So why did we not apply this formula? Because these two items, these two quantities are not given in the question. This information was not provided in the problem. We don't have the probability of A given B, and we don't have the probability of B. The probability of A given B is the probability that the first is successful given that the second is successful. We don't have that. We have only the opposite conditional probability, and we don't have the probability of B, the probability that the second is successful regardless of anything else. This information is also not given in the problem, so we just apply the multiplication rule depending on what information was provided in the question. Usually these kinds of problems can also be solved using a tree. So if we draw a tree, we know that we have two stages, the first stage and the second stage. Now if we consider the first stage, we have two possibilities, successful or not successful, like success or failure. And on the branch we put the probability that the first is successful is 0.9, which implies that the probability that the first one is a failure is 0.1. Now that 0.1 is not given in the question, but it's implied from the number. So if the probability of success is 0.9, it means the probability that the first one is a failure is 0.1, just 1 minus this, because the probabilities, these two probabilities have to add up to 1. Now given that the first is successful, since we start from success of the first stage, given that the first is successful, the second stage here has two possibilities, success or failure, and the probability of success is 0.95. And whatever we put on the second arrow here, whatever we put on the second branch, is a conditional probability because it starts with the success of the first stage. So the probability that the second stage is a success, given that the first was a success, is 0.95. And this implies that this probability is 0.05. 1 minus 0.95 is 0.05. This is basically the probability that the second stage fails, given that the first one was a success. And this number, again, 0.05, was not given in the question, but it is implied. We don't need it here, but we would have needed it if we have a question about failure. In any case, what was the question again? What is the probability that the first is successful and intersection the second is successful? This is what we want. And if we just use a tree, we just need to multiply the branches that go through success. Second successful and the first is successful, so we multiply. What we're doing is we are implicitly applying the multiplication rule, because what you see here, 0.95 is a conditional probability multiplied by the marginal probability. We are precisely applying the multiplication rule, and if we multiply these numbers, it gives us the intersection, and this is what we want. However, once we draw a tree and we get familiar to this, we can just multiply the branches. 0.9 times 0.95, it gives us the same answer, 0.855, as we have seen in our solution. Now let's go to the next topic, the total probability rule. Now the idea of the total probability rule is to calculate a probability in case we have different cases. Now imagine the following as a motivation, and then we go to our actual development. So if you take a course, let's assume that you have two possibilities. You study well or you don't study well. So these are the two possibilities. You study well or you don't study well. And in addition to this, you want to calculate the probability of something else. Let's say you want to calculate the probability of getting an A in the course. You want to calculate the probability of getting an A in the course, which is another event. So you have study well, not study well, but you have another event like the probability of getting an A in the course, and this is what you'd like to calculate. Logically or intuitively, what is the probability that you study well in the course? It's the probability that you study well. What is the probability that you get an A in the course? What is the probability that you get an A in the course? It is the probability that you get an A and study well, plus the probability that you get an A and don't study well, because these are two possibilities basically. You may study well and still get an A, or you may study well and get an A, or you may not study well and still get an A. So that's why maybe we can imagine it is logical or intuitive that the probability of getting an A will have two components. It is the probability of getting an A while studying well, plus the probability of getting an A while not studying well. And this is precisely what we have. So instead of using this picture, let's go to my own notes here so that we talk about the setup and the small proof. And then at the end, we will solve an example basically that will clarify the importance of this, and it will also clarify that it's not that hard. So although the equation that we will reach the probability of event B is equal to this long formula, this is what we call the total probability rule. We call it the total probability rule because we're adding up several terms. Although it looks a little bit complicated, however, it's not. It has a nice structure, it's easy, and even using the tree diagram, we can apply it automatically once we get used to this. But before that, let's talk about the proof. Where is this coming from? So what is the setup? The setup is, again, we have a random experiment, and this random experiment comes with a sample space, the set of all possible outcomes, and let's basically illustrate this using the big rectangle outside. So this is the sample space of a random experiment. Now this sample space is divided into mutually exclusive events. So we have event E1, we have event E2, we have event E3, and so on, lots of events until event EK. These events E1, E2, E3 until EK are all mutually exclusive. They don't intersect with each other. Any two of them are not intersecting. In addition to this, they cover completely the sample space S. So we say E1 and E2 until EK are mutually exclusive. They don't intersect. And secondly, they are also exhaustive. They exhaust the whole sample space. They cover it all. Let's have a peek at this picture here. This is an example here. So we have our sample space, the big box outside, and this sample space is divided into E1, E2, E3, and E4. These events E1, E2, E3, and E4, obviously they are mutually exclusive. They don't intersect. At the same time, they cover the whole sample space. Okay, so this is what we have. We assume that our sample space is divided into events E1, E2, E3, and so on until EK. In addition to this, we have another event. Let's call it B here. So this oval here represents an event B, and our target is to be able to come up with an expression for the probability of B in terms of the probabilities of the other events, E1, E2 until EK. Now, to do that, let's do the following trick. This event B here, this event B, how can we express it? First of all, what is B intersection E1? This was E1, so the whole part here is E1. What is B intersection E1? It is this shaded region here. So this shaded smaller set is B intersection E1. B intersection E2 is the other shaded area. B intersection E3 is the third shaded area, and so on. B intersection EK is this shaded set here. But if I take the first shaded set union with the second shaded set, union with the third, and so on. If I do the union between all these smaller events, E1 intersection B, union with E2 intersection B, union with E3 intersection B, and so on, union with EK intersection B, isn't that giving us B itself? It gives us B itself. We can also see it from here. So E1 is the whole thing here. This is E1. And what you see in the green area here, this represents E1 intersection B, or B intersection E1. The second green area is B intersection E2, B intersection E3, B intersection E4. If we do the union of these intersections, so B intersection E1, union with B intersection E2, union with, and so on until union with B intersection E4, the union of these smaller sets gives us the whole set B, isn't it? So this is what we have. Okay, so B is equal to E1 intersection B, union with E2 intersection B, and so on at the end, union with the EK intersection B. Now, what is the reason for doing that? Maybe you can feel this is something strange. So on the left, we have B, which looks nice and clean and small, and on the right, we have a long formula. Why are we doing this? We are doing this because these components, E1 intersection B, and E2 intersection B, and so on, are all mutually exclusive. So if E1 is mutually exclusive with E2, it means that E1 intersection B and E2 intersection B are also mutually exclusive. So these events are all mutually exclusive. And if they are mutually exclusive, it means if you want to calculate the probability So if we take the probability here, the probability of the whole formula of the whole equation, probability of B is equal to the probability of the first term plus the probability of the second term. We are allowed to add probabilities as long as the events are mutually exclusive, and we have seen that last time in the axioms of probability. So the probability of B is equal to the probability of B intersection E1 or E1 intersection B, it doesn't matter, plus the probability of E2 intersection B, plus and so on, plus the probability of EK intersection B. Isn't that right? So this formula here, this equation, is an equation on sets. So it's a set equation. This is a set, and these are sets. But once we take the probability, this will be a numeric equation. So these will be numbers. The probability of B is equal to the probability of E1 intersection B plus the probability of E2 intersection B, and so on. Now we are almost there. Not quite, but we are almost there. What is the last thing that we can do? How can we replace the probability of E1? Sorry, how can we replace the probability of E1 intersection B? Yes, using the total probability rule. The probability of E1 intersection B or B intersection E1 is the probability of B given E1 times the probability of E1. So the first term is equivalent to the probability of B given E1 times the probability of E1 using the multiplication rule. Also, the second term using the multiplication rule is the probability of B given E2 times the probability of E2 plus all the terms. At last, the final term is the probability of B given EK times the probability of EK. What you see here, probability of B equals to these terms. This is what we call the multiplication rule. So this is the multiplication rule, and this is what we can apply to calculate probabilities in terms of some other probabilities. Now, what is this here? What is this case? This is just the case if the events E1 and E2 until EK are just 2. So imagine here that we have just E1 and E2. We have E1 and E2. Obviously, in this case, the probability of B would be the probability of E1 times, the probability of B given E1 times the probability of E1 plus the probability of B given E2 times the probability of E2, and we stop here because the number of terms depends on the number of events that we have as mutually exclusive events. So this would be the case, and it's clearly true. However, we also know that if we have two events that are mutually exclusive and cover the whole sample space, then one of them must be the complement of the other. So here, instead of saying E1 and E2, we just call one A, and then the second one must be a complement because they are complement of each other, because they make up the whole sample space. So in that case, the total probability rule becomes the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. So it's exactly the same as the general formula, probability of B given E1 times the probability of E1 plus the probability of B given E2 times the probability of E2, but we just have a special case. Since we have only two mutually exclusive events, then one of them is the complement of the other. So instead of using E1 and E2, E1 is just called A, and E2 must be a complement. However, it is nothing new. You can really get along and solve everything by just using the general formula. Just the number of terms will depend on the number of events that you have, the number of mutually exclusive events that you have. Now let's solve an example here. So in this example, again, this example is coming from the book, and usually they can be simplified. And let me simplify it in this video here. And in exams, the expression of these problems will also be simplified, so they will be stated in the most straightforward way. Now, we have basically a material, and that material may have levels of contamination, talawuth, contamination. So we could have a high level of contamination or a not high level of contamination, and these two cases happen with these probabilities, and this is just given. So the probability of having a high level of contamination is 0.2, and the probability of not having a high level of contamination is 0.8. So the probability of high contamination 0.2, and the probability of H complement not high level of contamination is 0.8. Again, this is just given. In addition to this, we are talking about failure of this material. Sometimes this material fails if it has high level of contamination, and even if it does not have high level of contamination. So what are these probabilities here? These are conditional probabilities, and and this needs to be given to you in a straightforward and clear way. So we say 0.1 is the probability of failing given that we have high level of contamination, and 0.005 is the probability of failing given that we have not high level of contamination. So the probability of failing given high level of contamination is 0.1, and the probability of failing given not high level of contamination is 0.005, which is given in the number. So these are the two sets of information that is given. We have some marginal probabilities, the probability of high level, 0.2, the probability of not high level, 0.8. In addition to this, we have the probability of failing given high level is 0.1, and the probability of failing given not high level is 0.005. Now, what is the question here? The question, what is the probability that the material fails? Full stop. What is the probability that any material fails? Now, obviously, what this means is what is the probability that the material fails regardless of its level of contamination? It could have high or not high level of contamination. How can we calculate the probability of failing here? Obviously, this kind of question and the way it is expressed really calls for the total probability rule. And once you solve 2 or 3 exercises like in the tutorial and in the homework questions, you will get used to this. Once you see these kinds of things given, I think it becomes really clear that we apply the total probability rule. The probability of failing is equal to the probability of failing given high level times the probability of high level plus the probability of failing given not high level times the probability of not high level. So we just multiply 0.1 times 0.2 plus 0.005 times 0.8. We are applying the total probability rule, and we have 2 terms that we apply. This is how we solve the problem. Now, it really helps us if we use a tree diagram. And if we use a tree diagram, we can simply come up with this equation that has numbers without really having to think about the symbols. And it really simplifies how we solve the problem. So let's try to get familiar with how we draw that tree. So what do we have here? We have high level and not high level. We have high level and not high level. In addition to this, we also have some conditional probabilities. So we will have a tree that has 2 branches. As you see, we have a tree that has 2 branches. Obviously, in the first branch, we always have the marginal probability. So do we start with high and not high, or do we start with failing and not failing? We start with high and not high because this is the marginal probability. So if we have a material, imagine we have any material, the possibilities are high level of contamination with probability 0.2. So on the branch, we put the probability, and we have the possibility of not high level of contamination with probability 0.8. Now, if given that the level of contamination is high, it may fail or it may not fail. So F and F complement, fail and not fail. Failing happens with probability 0.1 because this is in the second branch that is coming out of high level of contamination. This probability is a conditional probability. It is the probability of failing given that we have a high level of contamination, which is here. Failing given that a high level of contamination, that's 0.1. Now, let me skip the red numbers for 2 seconds, and if the level of contamination is not high, the probability of failing given that the level is not high is 0.005. Again, this is a conditional probability because it's in the branch that is coming out of H complement, and it's precisely this probability of failing given not high level of contamination, which is 0.005, which was given here as well. Okay, so we have the first branch, high level, not high level, and the probabilities. And in the second branch, we have given high, failing, not failing, given not high, failing, not failing, and 0.1 and 0.005 were given in the question. Now, what is this 0.9? It just complements the 0.1. So if this probability of failing given high level is 0.1, then the probability of not failing given high level is 0.9. Just to complement, these 2 branches have to add up to 1. So these branches add up to 1. Whenever we have a branch, the sum has to be 1. So this is 0.9, and this probability, the probability of not failing given not high level of contamination, is 0.995, which is simply 1 minus 0.005. Now, we finished the tree. So what was the question? The question is, what is the probability of failing? Where do we have failing in the tree? Here we have a case. and here we have a case. So how do we solve the problem? We just add up the branches that lead to failing. This is one and this is the other. We add them up. 0.2 times 0.1, 0.2 times 0.1 plus 0.8 times 0.005. What we're doing here is exactly the same. We applied the total probability rule. Probability of failing given high. This is the probability of failing given high times the probability of high, plus the probability of failing given not high times the probability of not high. So we have essentially applied the total probability rule. However, if we draw the tree correctly, we can simplify our thinking and we don't have to really explicitly put all the symbols. It is just enough that we convince ourselves that we're basically tracing the branches until we go to fail. So we have fail here and we have fail here. So 0.2 times 0.1 plus 0.8 times 0.005. This gives us the probability of failing. Now I have a comment here. What if we wanted the probability of not failing? How can we solve that? Now I have two answers here. Maybe the answer that comes to your mind first, since we calculated the probability of failing already, we calculated the probability of failing here by tracing the yellow branches. Just 1 minus this would be the probability of not failing. This is correct. 1 minus the probability of failing is the probability of not failing, because this is a complement. It's true, and this is very easy to do as long as we calculated the probability of failing before. But what if the question was, what is the probability of not failing? So in the first place, the question is, what was the probability of not failing? Of course, you can tell me, I can get the probability of failing and then I do 1 minus at the end, or we can get also the probability of F complement from the beginning, from the first principles. How do we get the probability of not failing? This is a not failing, and this is also a not failing, and we trace the branches. 0.2 times 0.9 plus 0.8 times 0.995. So as you notice, we could have used these red numbers, which are not given in the question, in case we want something else, in case we are asking about the not failing. I hope that you understand that, and let's move on. Now we have the next concept is independence. We have been talking about two events here. We talk about conditional probability. What is the probability of an event given that we know another event has occurred, has happened? So we have event A and we have event B, like getting an A in the course and having studied, getting an A in the course and having attended all the lectures. This is a conditional probability. Now, since we have two events A and B, it could be the case that these events are independent of each other, which means they are not affecting each other. Now, before the formulas and how we check independence, let's make sure that we understand the concept. What is the meaning? The meaning that two events are independent. We say two events are independent if the occurrence of one does not affect the occurrence of the other one. They are not related in terms of occurrence. If one happens, it does not really affect the other. So the happening of the other is not related to the happening of the first, and vice versa. Let me try to give you an example on this. So we have the experiment of taking the course. We take the course, we have a lot of students. Let me say I focus on two students, student X and student Y, and I define two events. I define the first event that student X gets an A in the course. I defined a second event that student Y gets an A in the course. Let's call these events X and Y. So event X is the first student gets an A in the course. Event Y is the second student gets an A in the course. Let's imagine that these students are not relatives, they're not brothers and sisters, they don't study together, maybe they live in different countries because they take the course online as we have now, and they don't study, they have nothing in common. So we know they are independent. We know they are independent. Let's say student X gets an A in the course. Now, what about student Y? Does the fact that student A gets an A, that student X gets an A, affect student Y? No, it does not affect, because it's not related. This event is independent from the other. So this is the meaning of independence. Now, how can we check that two events are independent? So we have two events A and B, and according to this definition, and we will make sure that you understand it, that you make sense out of that. Two events A and B are independent if any one of these three formulas are satisfied. If any one of these three are true, they are independent. Actually, these three formulas are all equivalent, and if any one of them is true, it means A and B are independent. Let's look at the first one. So basically the first and the second are really intuitive and they make sense. So they prove themselves and they don't need any proof. It is just an intuitive idea. What was the meaning of the probability of A given B? It is the probability that A happens given that we know B has happened. Now, if B is not affecting A, if B and A are independent, isn't that probability the same as the probability of A? They have to be equal. This probability, this conditional probability, has to be equal to the marginal probability. Again, let's just review the meaning of the left and the right hand terms. The probability of A given B means the probability of A given that B has happened. But the probability of A is just the probability of A regardless of anything else. If B is independent of A, it means that the conditional probability needs to be equal to the marginal probability because the fact that B has happened does not affect the probabilities for A. So the probability of A given B is equal to the probability of A. If this is true, they are independent. Likewise, the probability of B given A is equal to the probability of B. By the way, this probability here, probability of B given A, does it calculate a probability for B or for A? It calculates a probability for B, given that we know A has happened. Now, if this is the same as just the probability of B, regardless of anything else, if these are equal, it means that A and B are independent. Now, what about the third formula? Where does the third formula comes from? It comes from any one of these two. How? Let's just look at this note here. So we have the first formula. Probability of A given B is equal to the probability of A, or probability of B given A is equal to the probability of B. If this is true or that is true, then A and B are independent. Now let's take any one of these two formulas. Let's take the first one. Let me rewrite the first one. So the probability of A given B is equal to the probability of A. That's the first condition here. Now what was this left side here? It's a conditional probability. What was the definition of the conditional probability? So let's replace this conditional probability by its definition. So we have the probability of A intersection B divided by the probability of B. So if you see this, it's exactly the same as the first condition. Now, if we multiply both sides by the probability of B here, what do we get? The probability of A intersection B is equal to the probability of A times the probability of B. And this is our third condition. If we notice that the probability of A intersection B is equal to the product of both probabilities, then A and B have to be independent. Then A and B have to be independent. So if the probability of A intersection B is equal to the probability of A times the probability of B, then they are independent. So we can, depending on what information is given to us, we can use any one of these formulas to check if two events are independent or not. Obviously, if two events are not independent, we call them dependent. So independent, the opposite of it is dependent. Now let me say a note here. In the previous lectures, we came across the idea of mutually exclusive. So what was the meaning of mutually exclusive? Two events are mutually exclusive if their intersection is equal to zero, not the product. No, it is just equal to zero. Two events are mutually exclusive. They have nothing in common. They are not intersecting, and the probability of the intersection is equal to zero, or the intersection itself is equal to the null set. This is the meaning of mutually exclusive. However, two events are independent if the probability of the intersection is the probability of A times the probability of B, not zero, but the product of the probabilities. Now, what is the difference between mutually exclusive and independent? Let's focus on the meaning. Mutually exclusive means the events are not intersecting. They have nothing in common. In other words, these two events cannot happen at the same time. If one event happens, the other one cannot happen, like the events of you getting an A in the course or you getting a B in the course. If you get an A, you cannot get a B. If you get a B, you cannot get an A. You get only one grade at the end and not two grades. These events are mutually exclusive. So the probability of getting an A and a B at the same time is equal to zero because this does not exist. But independent means something else. Independent means one event does not affect the other. So if one event happens, the other happens or not, it's not related. They can happen at the same time, but one event is not affecting the other. The occurrence of one of the events is not affecting the occurrence of the other. Okay, so this is basically the meaning of independence, and this is the difference between independence and mutually exclusive. It's a famous mistake. Mutually exclusive is not the same as independent. I hope that you concentrate and make sense out of this, and you will be more familiar if you start solving exercises. Now, let's extend the idea of independence to more than two events. If we have E1, E2 until En, so it's not just A and B or E1 and E2. No, we have more than two events. When are these events, E1, E2 until En, when are they independent? They are independent if and only if the following is true. If the probability of the intersection of all of them is equal to the product of all probabilities. So it's basically an extension to the third condition here, the probability of A given B. Let me give you an example. Let's say we have three events, A, B, and C. When are A and B and C independent? All of them are independent of each other if the probability of A intersection B intersection C is equal to the probability of A times the probability of B times the probability of C, and this extends to any number of events in case they are independent. Now, how can we use the idea of independence? We have this example here. So let's cover this example, and it uses the idea of independence. In this example, we have a system that represents any engineering system. Like if you have an air condition, we might connect a second air conditioning unit in parallel, so that basically we have a backup, so that the first operates as a backup to the second and vice versa. The good thing about that is that if one of them fails, the other one still operates, and vice versa. If the second one fails, the first one operates. So the basically the probability that the whole thing, the whole system will operate successfully, the reliability of the whole system will improve because we have a backup system. So this is basically the background or the idea of this example. But what is this example itself? The example says the following circuit here, the following circuit operates successfully if there is a path of functional devices from left to right. So if we can go from point A to point B through functional devices, through operational devices, through devices that have not failed, as long as we can reach either from the top or from the bottom, it means that the whole system operates. Now, the question also gives us the probabilities that each one of these components operate successfully. So 0.95 is the probability that the top component operates successfully, and 0.95 is the probability that the bottom component operates successfully. In addition to this, it's also given to us that these two devices fail independently. So the failure of these devices are independent. So the failure of one will not affect the failure of the other. Obviously, that the operation of these devices is also independent. Now, what is the question? The question is, what is the probability that the circuit operates? What is the probability that the whole system operates successfully? How can we calculate this? When will it operate successfully? Is it necessary that the top and the bottom have to operate at the same time? Is this really necessary? What happens if one of them fails? If the bottom one fails and the top one operates, the circuit is operating, and vice versa. If the top one fails and the bottom one operates, the circuit is operating. So the probability that the circuit operates is really the probability that the top operates or the bottom operates. It's not an and here. It's not an and, it's an or, because obviously either one of them, if either one of them operates, then the whole system will be operating successfully, and this is due to the fact that they are connected in parallel. Okay, it's due to the fact that they're connected in parallel. So what we want to calculate is the probability of the top or the bottom operates. Now, this is one way to solve the problem. I have another alternative way which I find easier, and let's focus on that. So the probability of the top or bottom, or is union. So what we need is the probability that the top operates union the bottom operates. How can we calculate the probability of the union? From last time, from the previous lecture, we have only one formula: probability of top plus probability of bottom minus probability of the intersection minus the probability of the top intersection the bottom, right? Are these probabilities given? Probability of the top is 0.95. Probability that the bottom operates is 0.95 as well, but we don't have the probability of the intersection. It is not given in the question. However, what is given in the question? It is the fact that the operation of these components or these devices are independent of each other. Since T and B are independent, so from independence of the top and the bottom devices, how can we express the probability of the intersection? Remember, using the conditions of independence, the probability of A intersection B is equal to the probability of A times the probability of B. If this is true, they are independent. If they are independent, this is true, right? So what we can do here is that we can replace the probability of the top intersection of the bottom with the probability of the top times the probability of the bottom, which are 0.95 times 0.95. So if we substitute here 0.95 plus 0.95, the first two terms, and then minus 0.95 times 0.95. So the only remaining task is to do this calculation. Obviously, this is a multiplication, so we have to do it first. 0.95 times 0.95, and then we add the terms and subtract, and the answer is 0.9975. So as a final comment on the meaning of this, because it's not just about solving a mathematical problem, it's also to make sense out of it. So what was the probability that either one of these components operates? 95%. So 95% this component will operate successfully, and 95% this component will operate successfully. But once we have them in parallel here, what is the probability that the whole system operates successfully? It is 99.75%, which is significantly more than the 95%. At least it is more than the 95%. So our reliability, our probability that we are still continue operating successfully has increased. And basically, one of the good things about this course is that we can use these arguments to do calculations like this. So this is a proof. If we put two things in parallel, why does the reliability or the probability that we continue operating successfully, why does it increase? We have just seen a certificate to this, right? We have seen a case here. So 99.75% or 0.9975 is the probability that the top or the bottom operates. Let me stop here, and in the next lecture we will talk about Bayes' theorem. Thank you so much. Assalamu alaikum wa rahmatullah.